I folks have discussed electromagnetism in one of my earlier videos. In that video, I briefly discussed history of the birth of electricity and magnetism. James Maxwell's equation is the integral form that explains how the electric charges and electric currents produce magnetic and electric fields. The equations describe how the electric field can create magnetic field and vice versa. Let me link the video in case you want to watch it. Please share and support my channel by subscribing. Click the bell icon for future videos. If you like the video, please give a thumbs up. My daughter and I produce these videos for information only, and there are no financial gains but just curiosity. We normally take it for granted radio and microwaves. For example, astronomers use radio telescopes to look toward the heavens to view planets, comets, giant clouds of gas and dust, stars and galaxies. By studying the radio waves originating from these sources, astronomers can learn about their composition, structure, and motion. Radio astronomy has the advantage where sunlight, clouds, and rain will not affect the observations. Now, let's dive into the subject.
Radio waves have the longest wavelengths in the electromagnetic spectrum. They can range from a length of a football to larger than our whole planet. Heinrich Hertz proved the existence of radio waves in the late 1880s. He used a spark gap attached to an induction coil and a separate spark gap on a receiving antenna. When waves created by the sparks of the coil transmitter were picked up by the receiving antenna, sparks would jump its gap as well. Hertz showed in his experiments that these signals possessed all the properties of electromagnetic waves. Radio properties. The low energies of most radio waves mean that they can be produced by a wide variety of different natural processes, often involving changing electromagnetic fields. Just to clarify, wavelengths can range from 1 millimeter to infinity. They have little or no effect on objects they encounter, but their long wavelengths make hard to disrupt, passing through and around most obstacles. This makes them ideal for sending signals at the speed of light. A radio transmitter is essentially a long antenna within which high-frequency alternating currents send electrons vibrating up and down. The receiver has tunable resonant circuits with an antenna of its own. Electrons will vibrate in the antenna when influenced by a passing radio wave of the selected frequency, generating a current that mirrors the original signal and can be used to reconstruct sound waves, pictures, or digital data. A very large telescope. To make a clearer or higher resolution radio image, radio astronomers often combine several smaller telescopes or receiving dishes into an array. Together, these dishes can act as one large telescope, whose resolution is set by the maximum size of the area. For example, if we were to look at the sky with a radio telescope tuned to 408 MHz, the sky would appear radically different from what we see in visible light. Instead of seeing point-like stars, we would see distant pulsars, star-forming regions, and supernova remnants that would dominate the night sky. A microwave is something you are familiar with. Images as they are used on TV, weather, news, and you can even use microwaves to cook your food. Microwave ovens work by using microwave rays about 12 centimeters in length to force water and fat molecules in the food to rotate. The interaction of these molecules undergoing forced rotation creates heat, and then the food is cooked. Wavelengths are 1 millimeter to 1 meter. These are the highest energy radio waves with unique properties. They interact more with the matter, A microwave oven, for example, traps microwaves in an isolated cavity where they cause the molecules in the food to vibrate, heating them up. They can be transmitted in highly directional beams, but are blocked by large obstacles and can only travel by line of sight. Microwaves are generated in devices called magnetrons, which cause electrons to follow spiral paths and generate currents that produce oscillating electromagnetic disturbance at the right frequency.
I'm trying to keep the video short, so I try to conclude with a little bit more on microwaves. Microwaves are a portion or band found at the higher frequency end of the radio spectrum, but they are commonly distinguished from radio waves because of the technologies used to access them. Different wavelengths of microwaves provide different information to scientists. Say medium length, that is C-band, microwaves penetrate through clouds, dust, smoke, snow, and rain to reveal the Earth's surface. L-band microwaves, like those used by Global Positioning System (GPS) receiver in your car, can also penetrate the canopy cover of forest to measure the soil moisture of rainforest. Most communication satellites use C, X, or Q bands to send signals to a ground station. In 1965, using long L-band microwaves, Arno, Penzias, and Robert Wilson, scientists at Bell Labs, made an incredible discovery, quite by accident though. They detected background noise using a special low noise antenna. The strange thing about the noise was that it was coming from everywhere, every direction, and did not seem to vary in intensity much at all. If this static were from something on our planet, such as a radio transmissions from nearby airport control tower, it would come only from one direction, not everywhere. The Bell Lab scientists soon realized that they had serendipitously discovered the cosmic microwave background radiation. This radiation, which fills the entire universe, is a clue to its beginning, which is known as Big Bang. I hope you love this video. Stay tuned for my X-ray and gamma ray in my next science video. Thanks for watching. Cheers and bye.